Okay, so now we know what empirical formulas are. That's great, but what if someone asks us to find the empirical formula for something? Well, there are a couple of different ways to go about this, depending on what our starting information is. So let's say, for example, if you're given a chemical formula for something, so you already know the existing chemical formula for the substance, and someone asks you, or the textbook asks you, to find the empirical formula, all you're really doing in that case is finding the simplest ratio. Okay, the simplest whole number ratio between the numbers of elements in the compound. And so how we would do this normally is we want to identify the greatest common factor between those numbers, and we want to divide by it. Okay, it's just like reducing fractions. This is your basic, junior high level math, or even lower than that in terms of the mathematics of this. So I have here a chemical which is entirely made up, fictitious. I don't believe this really exists. I based this on a real chemical, but it's a multiple of it, and we'll find out what that real chemical is when we actually derive the empirical formula for this chemical. So right now the ratio between the elements for carbon to hydrogen to chlorine is 42 to 27 to 15. Okay, so I have a chemical formula. I want to find the empirical formula of this. So I need to know the greatest common factor between these numbers. Well, I noticed that these are all divisible by 3. And in fact, 3 in this case will be the greatest common factor. So I need to divide all of these by that number. And this ratio will reduce to 14 to 9 to 5. And I know I'm at the simplest whole number ratio at this point because there are no more common factors other than 1. And so this will not reduce any further between these 3 numbers. So I know I've reached my simplest ratio possible. I've come up with the empirical formula values, in fact. So the empirical formula for this compound would be C14H9 Cl5. And this, in fact, is a real chemical. This is DDT. Now, many of you may not be familiar with DDT, but when I was going through high school, it was a big talking point, okay, as far as the environment is concerned. DDT is a pesticide which they used to use to keep mosquitoes and other insects like that under control. But it had some environmental side effects that they became aware of later. The DDT would get into the water supply and be taken into fish, and then birds of prey which lived on fish like eagles and osprey and so on would eat the fish. And the DDT actually ended up causing their eggs, the shells of their eggs, to be weakened and to break very easily. And so they were not able to have to reproduce as effectively as they normally would be. A lot of the eggs were not viable. And so bird populations started to drop, and they figured out that this was because of this chemical DDT. So it's not used anymore for that reason. But this is actually the formula for that. So if you're given the chemical formula to start with, then finding the empirical formula is relatively simple. You just find the greatest common factor, divide all those numbers in the chemical formula by that common factor, and then express the new ratio, okay, or the simplified ratio, to get the empirical formula. What's more common and maybe more applicable to real life are examples like the following. In a lab, an unknown chemical sample is analyzed. It is found to contain 4.731 grams of aluminum, 8.433 grams of sulfur, and 16.836 grams of oxygen. What is the empirical formula of this substance? So this is more like what would happen in a real lab. You have an unknown compound. You want to know what it actually is, what it's composed of. So you break it down, you weigh the different components that it separates into, and you find those masses. Now, we already have here, we have a ratio between these masses. We have, 4.731 grams of aluminum to this many grams of sulfur to this many grams of oxygen. We could express that as a ratio. We could compare those. But the empirical formula does not rely on mass ratios. So we can't just put these numbers together and come up with the empirical formula. But these are molar ratios. There are this many moles of this element compared to this many moles of this element compared to this many moles of this element in 1 mole of the entire compound. Okay, so we're looking to find the empirical formula, what we really need are molar ratios. So how can we find molar ratios in this case? Well, if you remember, we've been converting grams or various quantities of mass to moles already, so we know how to do that. So we can take these masses, convert them to moles of the substances, and then compare those molar amounts to find the molar ratio. Okay, and that will give us the empirical formula. So let's take a look at how this works in effect. So for the aluminum, I have 4.731 grams. And in aluminum, there are 26.98 grams of aluminum per mole. So that means this much aluminum, okay, this mass quantity of aluminum is going to be equivalent to 0.1754 moles of aluminum. So there, I have one number for my molar ratio already. Okay, for the sulfur, we start with 8.433, or we find that there are 8.433 grams of sulfur. And for sulfur, the molar mass is 32.06 grams per mole. So this is equivalent to 0.2630 moles of sulfur. And then for the oxygen, finally, 16.836 grams of oxygen. There are 16 grams per mole, which means that this quantity of oxygen is equivalent to 1.052 moles of oxygen. So now I have numbers that are comparing moles. This is my molar ratio, 0.1754 to 0.2630 to 1.052. Okay, but there's a problem still. This is not a whole number ratio. It's not the simplest ratio in terms of whole numbers that we could come up with. So we need to somehow convert these to whole numbers. So how can we do that? Well, remember, you don't change a ratio if you divide everything in it or multiply everything in it by the same value. So just like with fractions, if I divided all of these by 3, I actually have the exact same ratio as here. If I multiply all of these by 6 or 9 or 37.5, whatever number you like, I still preserve the ratio. I still preserve the proportionality between the various components of the ratio. So the easiest way to do this here, when I get numbers that are fractional, that are not nice and not whole numbers, not nice round numbers, is to take the smallest value of the 3, okay, which in this case is 0.1754, and divide all of them by that. You'll see why we're going to do this in a minute. When I do that, it doesn't necessarily help with these two, but when I divide something by itself, I just get 1. So this is the same ratio as 1 mole of aluminum compared to 1.499 moles of sulfur, okay, which is so close to 1.5 that we're actually going to call it 1.5. Okay, again, the error is only because of imprecision in our measurement or some slight lack of accuracy. But we basically assume, we know that in real compounds, we're not going to have, fractional parts of some molecule. You're not going to have half of a hydrogen or 0.43 hydrogens. So you have to have a whole number. So 1.5 is not still a whole number, but it's reasonable to round this to that. Okay, and then this division gives us 5.997 moles of oxygen, which is, again, just like with the previous example, is basically 6. So this is the same ratio. Okay, these strange looking numbers, when I pull this trick, this actually reveals that this is the same ratio as 1 to 1.5 to 6, which is much better. It's much more understandable, much more comprehensible for us. But it's still not all whole numbers. I still have one number here that doesn't satisfy that. So again, I can multiply or divide by anything that will change this to a whole number. So this is a half. 0.5 is half of something. So if I multiply this by 2, all of these will become whole. So 2 times 1 is 2. So this is the same ratio as 2 to 3 to 12. And that's actually going to give me my empirical formula. Okay, this is the simplest whole number ratio. There are not any common factors between these. I can't make this any simpler or reduce it in any way. This is the simplest whole number ratio of these chemicals in this particular compound. So what compound is this going to be? Well, I have 2 aluminums. Okay, remember this 2 is coming from here, from the aluminum atoms. So I have 2 aluminum, 3 sulfur, and 12 oxygen. Okay, that is basically my imperial formula. Imperial. This isn't Star Wars. That is my empirical formula. But being clever, I know that sulfur and oxygen tend to combine as sulfate. So actually here, this relationship between the sulfurs and the oxygens, what's really going on, because I know my oxyanions, is that S3O12 is really SO4, it's sulfate, but there are 3 of them. Okay, and if you did the oxidation number analysis of this, you'd see that this works out perfectly like this, because aluminum is going to be +3, sulfate has a -2 charge. So when I crisscross these, I'm going to get the charges adding to 0. So I can use my, my background knowledge of oxidation numbers and of the various types of ions, polyatomic ions that we have, to sort of take this a step further. Okay, would I expect you to necessarily be able to do this? No, not so much. I might ask you to do something like that as a bonus type question, but this you should be able to get here at least, okay, to knowing the actual ratio. Okay, let's look at one more example. 100 grams of aspirin, or acetylsalicylic acid, is the chemical name for aspirin, the compound in aspirin. 100 grams of aspirin contains 60 grams of carbon, 4.480 grams of hydrogen, and 35.53 grams of oxygen. Okay, what is the, I forgot to write the question, what is the empirical formula for aspirin? Well, again, to find the empirical formula, I need molar ratios. And these are still not in moles yet. Okay, I have masses. So we'll do the same trick as on the last one. I'm going to convert all of these to moles. So the carbon has a molar mass of 12.01. per mole. The hydrogen has a molar mass of 1.008 grams per mole. The oxygen has a molar mass of 16 grams per mole. Okay, these 3 values at least, and probably nitrogen as well, you should basically memorize these molar masses, because carbon, hydrogen, and oxygen are in so many compounds. You're going to be using these over and over again. Just get these ones down. It will save you a little bit of time and effort from having to go back and check your periodic table every single time. So when I do the calculations here, I end up with 60 grams of carbon is equivalent to 4.996 moles of carbon. 4.480 grams of hydrogen is equivalent to 4.444 moles of hydrogen, and 35.53 grams of oxygen is equivalent to 2.221 moles of oxygen. Okay, I'm keeping 4 significant digits because I have 4 significant digits in these measurement values. Okay, again, these are not whole number ratios. This is the molar ratio, I've got that, but it's not the simplest whole number ratio. So again, I need to pull this trick of reducing one of these to 1 so that I at least have a 1 whole number to kind of start with. And if you're looking closely here, you will see that actually, in this case, it's relatively easy to see that this is this one is approximately 2 times this one. So I should expect a proportionality here of 2 to 1. So if I divide all of these by the smallest value, which in this case is 2.221, this is going to simplify things a bit for me. That gives me 1 mole of oxygen for every, this comes out to be just about 2 moles of hydrogen. And this division gives me 2.25 moles of carbon. So my ratio in aspirin is 2.25 carbons, that should just be a decimal point, to every 2 hydrogens to every 1 oxygen. So this is my molar ratio. It's still not whole numbers though. Okay, again, I can multiply this by something that will make these into whole numbers and still preserve the ratio. So here I have a 0.25. This is a quarter. This is the fraction a quarter. So I will multiply everything by 4 to turn this into a whole number in this case. So 4 times 2.25 is actually 9. 4 times 2 is 8. And 4 times 1 is 4. So I have 9 carbons for every 8 hydrogens for every 4 oxygens. So the empirical formula for aspirin is C9H8O4. And in fact, this is the actual chemical formula for aspirin as well, although we wouldn't be able to know that simply from this information. All we can find given this is the empirical formula, but it just so happens that in the case of aspirin, that is also the chemical formula. Okay, so this can be a little bit tricky. We'll still continue to use this a little bit in the percent composition problems that we work tomorrow. So I actually realized that I should have mentioned this before I ended the last video, but so I'll just comment it quickly and then I'll splice it into the regular video feed. I'll edit it into the proper place. But what if you're doing finding an empirical formula like this, and these numbers that you have here when you calculate the molar ratio, what if they come out to already be whole numbers? Like what if you did this and it came out to be 5 to 4 to 2 or something? Well, that's fine. Like that's great actually, because then you don't have to do any of these extra steps of trying to take the ratio and convert it into whole numbers. Like they're already whole numbers. So you're already done at that point. You actually just finished the problem. So if I did these calculations and I ended up with some whole number ratio here with these numbers, they were all whole numbers already, or they were all very close, like here 4.996 is very, very close to being 5, and maybe this one was 3.96 or something like that, and this one ended up being 2.013. Okay, these are all so close to being whole numbers that we can assume that the error is based on problems of measurement and not on the actual mathematics of the problem. So we already have whole numbers in this case. We have 5 to basically 4 to basically 2, and we can just stop there. That is going to be our molar ratio. That is going to give us our empirical formula. So if those were the numbers, we would just at that point write C5H4O2, and we'd call it good, because this doesn't simplify any further. It's the simplest ratio, and it's all whole numbers. So we have what we want. Remember, that's what the empirical formula is. It's the simplest whole number ratio between the elements.